Hello, welcome. Let's get started with 2.1. Now, section 2.1 is sort of divided into two parts. There's the matrix vector product that we're going to look at right now. And then we're going to sort of take a break and look at linear transformations. And then we're going to see how, they're actually kind of the same thing. So here's this definition here. So suppose A is an R by C matrix. So it has C columns. C is the number of columns. And each one of them has R rows, R entries. And if X is a vector in RC, meaning the same number of columns that you have is equal to the number of entries in X, then we can define this product AX to be the linear combination of the columns of A using the corresponding entries of X as weights. So the first entry in X scales the first column of A. The second entry in X scales the second column of A, yada, 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 up to the entry number C of X scales column number C of A, and you add them all together. And what you get is a vector, because a linear combination of vectors is always a vector, in R. In other words, a vector with R entries in it, because each of the columns of A has R entries in it, because that's how many rows of A there are. When you combine them, you get a vector with R columns. Okay, let's look at an example. So here we have the columns are the vectors 1, 4, 2, 5, and 3, 6. And these are the three entries in X that we're going to multiply them by. So that gives you negative 3 times 1, 4, plus 1 times 2, 5, plus 1/3 times 3, 6. And you could write this, if you want, as negative 3 times 1, plus 1 times 2, plus 1/3 times 3 as the first row. Same idea with the second row. And the result is the vector 0, negative 5. And here's, in part B, a differently sized thing. Here we have a 3 by 2 matrix A that we're multiplying by a 2 by 1 vector X here. And the important thing is that the number of columns here we have 2 columns, that agrees with the number of entries in X. So yeah, we can multiply this. We're going to get the first column of X scaling the first column. We're going to get the first entry in X scaling the first column of the matrix. And of course, 0 times anything is just 0. So we just get 10, 12, 14, like so. Okay, let's look at example 2. We're going to write this system of linear equations here as a vector equation and as a matrix equation, which means in the form a matrix times x equals y. Now, first of all, we talked a lot in chapter 1, but we can review it really quick, that this system of linear equations is equivalent to saying you have two vectors that are equal, like the vector on the left side, like so. And these are, of course, the same because these two vectors are equal to each other if and only if the first component on the left side is 4 which of course means the first equation in the system is true, and if and only if the second components are also equal, which means the second equation is true. So those are definitely equivalent, and the one on the left you could write as a sum of some vectors. And of course you can write each of these terms as a variable x1 or x2 times that vector. So we can write this as this linear combination, and then we can apply the definition of a matrix times a vector to say we have the columns pi 0, 2, -6, -1, 3, multiplied by x1, x2, x3, and that's equal to 4, 5. So the matrix A that we're talking about has these columns, and the Y is the 4, 5, and the X is X. Okay, so in general, if A is an R by C matrix and the columns are labeled A1 through AC, then the following are different ways of saying the same thing, just like this example. The vector equation, where these vectors are equal, but the definition of AX is that linear combination. So those are definitely the same thing. And the system of equations with this augmented matrix, we saw why that system of equations is like this vector equation. Now, I really want to emphasize that this is the thing we've been studying from the beginning. So like even in section 1.1, where we introduced this system of linear equations, this is the same thing as AX equals Y, because if the A which is the coefficient matrix, is written like this, and the X is, of course, just the variable matrix, then this is really just AX equals Y. So the left side of all systems of equations we've looked at this whole time is now going to be written as A times X. And this is kind of nice because writing out the whole system of equations was kind of a pain sometimes. It was a lot of writing. Even writing out the linear combinations like we did in 1.3 onward took a little bit of space. This is a thing that I think is really cool about linear algebra, is it gives you a lot of ways to take big complicated things like we've seen in chapter 1. There's a lot of complexity going on in a system of linear equations like this, and we can write it as this simple looking thing, AX equals Y, which is one thing that makes linear algebra kind of powerful, is without writing a lot, we can still describe a lot of math. So on the right side of this, what we have is kind of just a restatement of the stuff we did in chapter 1, just written in terms of a matrix times a vector. So the stuff that is in red here is just rewriting it that way. So here's a definition of a homogeneous system of linear equations. You can write it as a vector equation like that, or as a homogeneous matrix equation like this. Because again, what A times X means is by definition this linear combination on the left. They're the same thing. So that's a homogeneous matrix equation here. Okay, the solution set of that is called the null space of A. And again, we can think of null A as just the set of vectors x that you can multiply by A to get 0. Because what it means to multiply A by x is this linear combination. Likewise, the column space of A, remember, is the set of all linear combinations of the columns of A. Well, linear combinations of the columns of A, you can just write as A times x. So yeah, it makes the notation smaller, a little simpler, but we're still describing a kind of complicated thing. Now, likewise, we can also restate the existence and uniqueness theorems. Here's the existence theorem. One part of it says that every system of equations that has A as its coefficient matrix is consistent. Well, a system of equations that has A as its coefficient matrix is just AX, like we saw here. Like the coefficient matrix was the stuff on the left of this example, and that ends up being the A. Likewise, looking at the uniqueness theorem, the new thing we're adding is that if AX equals 0, then X equals 0. Well, the null space of A is the set of vectors X that satisfy the linear equation x1 a1 plus yada 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 plus xc ac. So this linear combination of the columns of A is just what we mean by AX. So yeah, a lot of things can be restated in this kind of more elegant notation. All right, let's go on to linear transformations in the next video.